All right. Good morning.
Morning, everyone.
Yeah. How is your Sunday, Igor?
Oh, Sunday, I'm not sure, but Saturday is good. Is good.
Exactly. um.
But last Sunday was okay. Yeah,
Huh? Sorry.
last Sunday was okay.
Yeah. Okay. Yeah. That was my question about. Indeed. Yeah.
Of course. Yeah.
um.
How is your Saturday?
Yeah. Well, good. I planned it a little busy today. So yeah, some activities with the family. Also some activities for myself. And we probably will have night code in the evening. So looking forward to this Saturday. A little busy, I think busier than usual. Um, but yeah, hopefully that will be all right. And we start
For sure.
with some brain exercise already this morning. So really curious to yeah, to catch up where we left it last time. Maybe we can recap it a bit and where we go, and that would be really nice. I looking forward to that, Igor.
Yeah. I also look forward to that, and yeah, I'm super impressed that you start your day or almost start your day with coding, and you probably will finish your day with coding. So it's very impressive. I admire. Yeah, and we are XTechnology. Yeah, I think we told it for quite a while. A community that it consists of people who are devoted to IT technologies, or not only IT, to different technologies. Yeah, we do webinars, we do projects, workshops, mentoring, and all these kinds of activities. And we have an awesome website, xtechnology.dev,
Yeah,
which you see on your screens.
yeah.
And
Please
please
follow
go
us.
there.
Share with your friends if you like the content. Put some likes on it. You know, it helps.
Yeah, would be awesome. Would be awesome. Okay, yeah. Then to the topic of our today's talk. Yeah, as Alex said, we already started doing it, I think, 2 months ago, maybe even more. I think even more. So that is about deep learning. And I'm a data scientist, but I mostly work with, as now people say, core ML models. So shallow learning, not deep learning. So usual models like logistic or linear regressions and random forests, all this kind of stuff. But now it's super trendy to read and to use all these large language models like ChatGPT, and also all these generative visual models like Midjourney are taking over. So that's why I decided that it's time for me to kind of catch up. I know that it's like a really big thing, but you have to start from somewhere, right?
Yeah.
Yeah.
But that thing that we did and that you're showing right now, how it actually relates to the deep learning, is that a part of deep learning or is uh, yeah, somehow it's how it's related?
Yeah. So here the main idea is to do an exercise, more or less. So first of all, we are using here the Python framework called Pytorch, and it's mostly used for creating deep learning architectures and networks and training the models. So that's one of the things. And another one that's usually when so there are some steps when you want to create your model, just a simple model or a deep learning model. And here we want to kind of recreate it almost manually, like with different steps. Usually in the project, you don't do it because more high-level frameworks already do it for you. But it's always nice to understand what it consists of. And here we will be using the very generic dataset, which is known to everyone in deep learning domain. So it's MNIST. So it's a set of handwritten numbers from, digits from 0 to 9. And the idea is to recognize them. This kind of dataset and the task of recognizing it's already solved by perfectly by all different kinds of models, but still it's a starting point, and you can always test your skills on this data set.
Nice.
Yeah. So yeah, I'm super far from being an expert in this topic. So I have my cheat sheet for this. So I sometimes will look there. And yeah, let's see how far we would get in this. Last time we got not super far. maybe.
I remember a little bit. We explored the library yeah, we explored the steps that you need to provide, and I remember we stopped somewhere with the iterations. Like I think you showed how to train, and I remember a little bit from my almost zero background that you need to train in generations your system or your model, and I think that's where we stopped, right?
Yeah, I think so. Yeah, you're right. I think what we did, we just imported the modules, and I kind of did it recently. So now we have the imported stuff, and we can do the same as we did last time. So we get the data. So this MNIST data set, it's already stored in a lot of different packages, and Pytorch also has it. So torchvision.datasets.mnist has the data, and now it's gonna download it, and it just did it. And we can just see how it looks like. So here we take just a random number 333 to 1.
I have a little side question, if you don't mind.
Of course.
Let's say we do this Python Jupyter notebook, right? Model. We complete our exercise, and what happens next? Like theoretically, can we compile it, or I don't know, it wrap it up in some executable, and then integrate it in any API? Let's say, is that how it works?
Yeah, sure. That's the main kind of question of what you're going to do with all of that. Surely, yeah. So as the output of our exercise, ideally, we should have a trained model that is ready for inferencing. And inferencing means that you send unknown data to this model, and it predicts the output. And yes, you can wrap it in the API. So the most common API in Python API framework is Flask. So it's very easy. So you can deploy this via Flask API. I mean, you can wrap it in the Flask API and deploy it somewhere. We can, yeah, I mean, it could be locally, or there are a lot of services, I don't know, like Heroku or Vercel, where you could do it. And also there are a lot of cloud services, which already...
Vercel is used for that environment as well. It's interesting.
No, I mean, Vercel is mostly used for bigger things, I think, than just deploying the model. But it could be used for this as well.
But output of this can be not only Python, right? You can do the executable out of it or not, or it should be Python in most cases.
That's a good question. For now, it's kind of Python. So, but still, when you create an API, the API receives the JSON usually, and what happens inside the Python runs, yes, but you also can kind of convert it, I think, to other languages. With this topic, I'm not super familiar. At least I know that there is this framework of library or Onyx or NX, which is able to convert models from different libraries to different libraries. I think it also could convert it from different languages, but I won't be super sure.
Okay. Yeah. Thanks for elaborating.
Sure. Yeah. Yeah, that's actually the questions that I would like to be able to answer myself, quite with confidence. So I'm getting there. Yeah. Yeah, I actually recently was interviewed for an MLOps position, and there were these kind of questions, and I kind of realized where are my gaps, and now I should cover them. So I guess that's the first or 1.5 step to get there.
Yeah, let's get there.
I wish, I hope that you help me there. Great. Yeah. So the data set, we have downloaded this data set into this object, data.mnist, and now we would just want to look at how it looks. I think there are 50,000 items in the data set, and we just take a random one, like 33,321. And every object consists of the image itself and the label. So the zeroth element is the image, and the first element is the label. So here we just see the image. hopefully. Yes, so it's 5. And if we output the first element, it should say 5. Yeah, so it's kind of the item and its label.
Mm-hmm.
Yeah, so as you mentioned before, so we do train the models in these iterations, which we call epochs. And one epoch means that we go entirely through the whole data set that we have. And we train the model on it. And then if you want to go further, we go again, and we can do multiple epochs. And the thing that the thing that we usually train it on GPUs, and GPUs has some memory that it's available. And the images, so you need to put the images to this memory, and also you need to have the weights of the model in the memory. So the weights is the thing that you are training, that you are changing during the training phase. And they might be really large. So for now, it won't be large, but if we take like these modern models, it could be just gigabytes of data. And you usually cannot put all of it to the memory, and you can put only a chunk of your data. So that's why there are so-called batches, and usually you train in batches. So you put, like the usual size of the batches, I don't know, 32, 64, the powers of 2. You put like 64 images to the memory, you train your model on the 64 images, and then you get the next batch. So it's kind of step by step. Yeah, and so for this, you kind of create separate objects in Pytorch that are able to handle the batches. I mean, you can always do it yourself, like say that this is my batch, first 64, and then you have to track this index where you are at. But Pytorch has a special object for it, not for you to care about it. Yeah, so first of all, let's re-download the data sets so that we have a train and validation data set, because now we just downloaded the whole data. And here we say, basically, these lines are the same, the first and the second, but in the end we say train equals true or train equals false. I think Pytorch just has these data sets already pre-configured, and they will get you the chunk of the data which is ideally should be used for training, and the second chunk which should be used for testing.
And it's randomized, sort of that, right? It doesn't matter from these data sets which portion you pick, and it should
I think it was kind of already randomized by them, and they already store it on their in the repository in such a format. So we can also do it ourselves, so we download everything and split it, but they did it for us.
Nice.
And also I think now we kind of downloaded it in a bit different format. So first of all, what's interesting, we can look at the lengths of our data that we downloaded. And I have to rename it. It's not DS training as well. Yeah, so it's 60,000 images for training data set and 10,000 images for validation. And I think what has changed here, so here we specify that we should use transform, and we say to tensor. So I think now we don't have an image like this, but we already have a tensor, like a 3D vector of this image. And let's check it. Again, let's take a random number. That's too much. And I think here we should have it. Yeah, so now we don't see the image itself. It was converted to a tensor. So a lot of different numbers. So it just represents the RGB of the image of the number that we have here.
Yeah.
Good. Yeah. So for now, we downloaded these tensors, and as I mentioned before, we have to work in batches. And here we've specified the size of the batch 128, and we create the so-called data loader object, which will handle this batch processing for us. So we just specify on which data set we want to do it and the size of the batch. And here we say, shuffling or not shuffling. And here we have two objects for training and for validation. While we train, we ideally want to shuffle the objects because we don't want our model to learn just the sequence of the numbers. We want it to train on random stuff. But when we validate the data, it doesn't make sense to shuffle because we just want to test how it works on the chunk of data that we left aside. And yeah, so let's just run it. Yeah, now we have these two objects, and basically we are ready to go to the next step. And the next step will be, I think all of it we already did, but still, hopefully today we get a bit further. Yeah, so the step now is to create the model itself. We will do just a very simple architecture.
A model of layers of this network, right? That's a model.
Yeah, exactly. So we just create here these sets of layers, and this is our model. So
yeah,
yeah, so we kind of say that we want a sequential wrapper over our layers, and sequential means just like one after another. And what we do here, yeah, we just first flatten all our vectors because we have 3D vectors, and we just flatten them to 1D. That's usually how you do it. Just put all the numbers together. And then we put a couple of linear layers. So here you have two parameters. The first parameter is like how many input, not numbers, but yeah, I mean input digits you will have, or the size of the vector.
Yeah, basically this is our image, right? Image, like how many pixels it contains, well, with the RGB, of course. Yeah.
Yeah, exactly. Yeah. So our image is actually, yeah, I was wrong. It's not an RGB. It's grayscale. So it's just one value per pixel, and the images are 28 by 28.
Okay.
So that's why this, yeah, the input size is 28 by 28. If it's RGB, then it would have been like this. Yeah.
Okay.
So here it's specified the input should be kind of fixed because we have images of predefined format, but the output is more or less what we want. So here I just say that I want the output of, that's, how much is it? 64, right? No, 32, yeah. My God. Yeah, so I'm just saying that the output should be 32, just because I want it. And so here we also introduce another layer. It has the same input as the output of the previous, and also random output because I just want it. And in the end, we just say another layer, which has, again, the same input as the output of the previous. And in the end, it has 10 elements because we want to classify the digits to 10 different numbers. Oh, digits, yeah. Yeah. And yeah, after every linear step, we have this relu element. That's kind of an element of non-linearity. So how these layers look like, you get the input to the layers, and then you sum these inputs with different coefficients. These coefficients are weights. And then after summing it up, you introduce some nonlinearity to the sum, because if you won't do it, it will be just a complicated linear model, and it won't even make sense to do all of it. And this nonlinearity, yeah, it could be a different function. It could be some exponent. It could be like that. We are kind of, yeah. It could be an exponent. It could be some, I don't know, module of the number. And relu, I think, yeah, I'm not sure if my browser will let me do it. Well, probably it will. Yeah. So relu looks like this. So basically, yeah, it's almost linear. I think this is 0 on the x-axis. So if our input element is more than 0, then we just output the linear, the element itself. But if it's less than 0, we output 0. And so this is kind of the nonlinearity that we introduce, and that's why we are able to kind of create a neural network.
Is there any semantic for below 0 here, or is just a function itself? I mean,
sorry, consider again.
Yeah, and like in this relu function that you show now, does below 0 mean something in our model as well, or it's just a function and we don't care what it is, what are the numbers?
More or less, it's just a function. So it's just a simple function that gets the input, and it says if the input is more than 0, we output the input. If it's less than 0, we just output 0. And yeah.
All right.
Yeah, it could be a bit modified. So you see it's some jello. I'm not sure what G means. So it's kind of a bit weirder shape, but I think this function, the green function, is differentiable. So you can differentiate this function. And with Relo, it's a bit harder to differentiate because of the 0 function.
Yeah.
Yeah, but still, I have to read about it, how they do it with Relo without a lot of effort.
Right.
Yeah, so let's just I create this model, and if we output, it will show us what it consists of. Yeah, input features, output features of every round, of every layer. And now we have a couple of things to add to it. So first of all, we should introduce the loss function. So when how all this works? So you have the structure of the neural network. You input your image. It goes through the layers, and all the weights are calculating the output. So at first, your weights are not trained. They are just random. And still you have some output. And then you have the real output. And you can calculate the difference between your current result and the output. And then you introduce some function, which is the loss. So how to calculate the loss given your output and the real output. And then you have this loss, and you send it back through the whole architecture and try to update the weights so that the loss is lower. So that's called backpropagation in my interpretation.
Yeah.
And so there are already a lot of different losses implemented, and a lot of them are used widely. And one of the most widely used is cross entropy loss. I can try to open it here. Let's see, cross entropy loss. Yeah. Do we have a function somewhere? Yeah, so basically, it looks kind of this. So you have your real value, and you have your predicted value, and that's just the way you combine them. So you go through the whole of your batch or data set, you calculate this formula, and in the end you get the loss. Somehow it's the most widely used loss for these kind of tasks.
All right.
Yeah, and the second thing that we have to do, we have to create the optimizer. So that's the thing which will be optimizing the weights. So it knows the loss, and it tries to optimize the weights so that the loss becomes lower. And it's already, again, kind of coded for us. I think one of the most famous is Adam. I think Adam means adaptive. I don't know what method for stochastic optimization. Yeah, to be honest, I don't remember what it means. But basically, it kind of does all the job for us of the optimization. So it gets, as an input, it gets all the parameters of the model, and it optimizes them on every step. Yeah, and it also has some parameters like a learning rate, so how fast you should update the weights, and you can tweak it. Yeah. Okay, so I think here we were on the last time.
Yeah.
So this time, hopefully, it's gonna be a bit quicker.
Yeah.
So here I'm just introducing. Yeah. Let's hope. So now is the most fun part where I have to write some code. So we just introduced 20 epochs just because we want. We could do one epoch. Well, let's do it. And so here I kind of commented the steps, what we should do. Why I said continue here. We actually didn't here. Okay, yeah. So how the training looks like? We iterate through the epochs. So one epoch is the whole run through the whole data set. And every epoch, we get the batch, we enumerate through the batches, we iterate through them. Then we do the forward pass, so we throw the batch into the model, get the output, then we calculate this loss given this output and the real values, and then we propagate it back. And on this, we propagate it back, and then we run the optimizer. It will optimize the whole structure. And yeah, basically we have to now implement it. And there's always a validation step to see like what are the metrics for your model. It's similar, but on the validation data set. Yeah. Yeah. So so let's kind of do it. I as I said, I have my cheat sheet, so I will look there.
Okay.
Because I'm not confident for me that I can do it from the first run. So our batch, training batch is DL train, yeah. So let's DL train. And I think when we iterate, let's do enumerate. Actually, enumerate. Yeah, in Python, if you want to get the index of what you're iterating over, you have to wrap it into enumerate. And then it would be like this.
Enumerate is a built-in operator or a function?
Yeah, it's a Python
Standard
function.
library, okay.
Yeah, because when you just do for something in something, it just goes over, but it doesn't output the index of this of the current iteration. And now we want to have it. Yeah. Okay, so now the forward pass should be train. Yeah. So basically, we have the model in here, and let's real value. So if we input it, output. I think it should be just as easy as this. So we just put the X element. Actually, usually we have it with a capital X. So we just throw the whole batch into the model, and the model output should be what we want in the end. And I think we can actually call it ycalc. Yeah, so that's y, that's our values, the calculated values. And now the loss function. Loss function already identified in here.
It's interesting that the loss function and optimizer are not part of a model.
Yeah, so that's kind of things that you can adjust. So you have the model, and you can optimize it differently, and you can calculate the loss also differently. But the model itself, it's just a set of the weights.
I see.
And these weights could be obtained by different ways with the help of this loss and optimizer. So now we have kind of to do the backprop. I think I'm kind of a bit slow in here.
We have the whole Saturday, don't worry.
Yeah, we have the whole Saturday. Yeah, I'm just looking. So criterion budgets, loss. I think basically we just can do the backpropagation, which will be, let's save it to loss. And now we do loss backward. And here we just do the optimizer step. Optimizer, is it? Optimizer. Optimizer step. I think kind of on a high level, it's what we can do. Almost, and actually we'll try to run it. Let's maybe do one. I hope. I just want to see if it's.
Wait 1 second. I'm trying to. I think. Do we miss something here? Because like when you calculate the loss, it's not related anyhow to the optimizer or model, isn't it? Just calculates it. That doesn't pass it to optimizer, for example.
I think that because we introduced optimizer so that its parameters are model parameters.
Yeah.
It should always know that it should optimize the model.
Yeah, but the loss itself is not used anywhere, as I see it.
I think it kind of is used. So here we took the model parameters.
Yeah.
And we ran we put the input into the model parameters and we'll get the output.
Yeah.
That's already kind of dependent on the model.
Mm-hmm.
And then we create another function which entangles this created thing, which depends on the model, with another value.
Yeah.
And then when we do backward, it kind of should throw all the calculations backward. And it's also dependent on the model, on the model that we identified. So kind of loss has model parameters as its kind of parameters. And the optimizer also knows that it should optimize the model parameters.
Maybe I'm totally wrong. But you see that when you introduce a loss function, for example, it doesn't. It seems to be just using a library, so it's just a function, right?
Mm-hmm.
The optimizer, I can see that you pass the model inside, so that's fine. It's related to a model. I can see that. But when you when you train the model, it seems that yeah, we got some output from a model. Got it? Wipe out. Then we calculate a loss with the loss function. We do it backward, but I don't see how this backward is related to a model. Is that because it's not part of a loss? Not loss is not using the model. But I'm not sure. I don't know how that works. But it seems to me they are not connected.
Yeah. I kind of totally share your concern. To me, it also looks a bit weird. Okay. But yeah, I think they are just connected because optimizer knows that it should look at the model parameters, and this loss also has been created as the combination of these parameters.
Okay.
Yeah. Maybe we can Google dot backwards. Pytorch.
Interesting. Yeah, it doesn't matter in our case, of course. It's not what we should be investigating, I guess.
Yeah, I mean, yeah. So let's backward computes all the derivatives for every parameter which requires grad true.
Yeah. What I would expect, you pass this loss somewhere into the model, maybe to the optimizer, because they're related.
Yeah, I think it would have been really logical if you pass this loss backward output to here.
Yeah, something.
I agree. Yeah, I agree that it would be logical, but somehow it's not like this.
Okay.
In this framework. Yeah. That's actually a good point. Yeah, I'm not sure why is this. Why is this so?
How does it work? Yeah, how does it even work?
Oops. Yeah.
Okay.
But I hope it should work. And so I just want to see if it works or not, or if it throws some error, because now it throws some error. Yeah, okay. I think what I didn't do yet. So now we have the X and Y. They are just tensors, but the model operates on the GPU. And we have to explicitly send these tensors to GPU. So for this, yeah, maybe. Yeah, so I think it's done like this. So x to there. Yeah, let's make it not capital. Just because. Yeah, and the same for y. So I think now we should not have this error. So I'm not entirely sure what happens here, but basically it takes the tensor and somehow sends it to the graphic processor.
Mm-hmm.
And okay, so now we have a different error. Or expect all tensors to be on the same device, but found at least 2 devices. Oh, CPU included 0. That's interesting. The 0, y calc. Should I be also put model x? Yeah, in my cheat sheet I have another layer, another string. Maybe it's kind of the reason where I specify that model should be in the train mode. I think that just means that it's in the train mode and that its weights could be changed or updated.
Mm-hmm.
And let's see if it helps or not. It does not. Just, yeah, first of all, are we on the GPU currently? Yeah, we're on GPU.
Okay.
Expect all hands to be on the same device, but found at least 2 devices, CPU included, when checking for the element. Maybe I specified it wrong. Q 0. I mean, I could literally do this. I'm not sure if it helps. No, it doesn't. Okay, so now I'm looking at my cheat sheet and.
I was looking also at some example. I think loss actually is not. You wrote it and explained it correctly, I guess, but I think loss would be used afterwards, after this iteration, when you actually will calculate the accuracy. And I think, yeah, I think it will be passed to somewhere to the model. But anyways, so yeah, yeah. I was also comparing the sort of cheat sheet that you have. I also opened some article, and it seems to be correct with what you're doing. Sorry.
No, yeah, I know what you mean. I hope that I understand what you mean. So the loss. I think that, yeah, the loss should also be maybe sent to CPU. Loss CPU. Oh wait, CPU. Now it's on GPU. Now it's on GPU. I hope. And it doesn't like this string, right? Like model train and model expected all tensors to be on the same device, but found at least 2 devices.
Interesting.
What am I doing wrong? Adding .CUDA, model.CUDA, function to add both the model. So the model should also be.
Okay.
Okay. Did I? Yeah, I missed it. I kind of in my cheat sheet I did it here, and here I kind of missed it.
You defined already where to calculate it. Okay.
Yeah, so that's what happens when when you're just copying the stuff.
That's a very interesting exercise for me. Like, see it probably third time in my life, sort of that code. but it seems straightforward with, of course, comments of an expert.
Yeah. All right. Okay. Now, hopefully, now we don't have an. Oh, we still have implemented for long. Why calc? Now maybe we have to send it back. This I'm not sure. It's criterion loss function. Costs of max not implemented for long. What? So X and Y are currently on CUDA. This stuff on CUDA as well, model on CUDA. Y calc. It's very interesting to do it live like this. Maybe I should have just taken my cheat sheet and implement every cell of it.
Yeah. It seems to me like that, this library, like I think I had this comment last time as well. Like, yeah, why to? Yeah, sorry. Probably it's for the usage that we do today. In this exercise, we could use something higher level model. Yeah, like that already contains all these settings inside, and it probably would be much easier than do it manually.
Yeah, I totally agree. It's just that I wanted to start with this exercise because it's kind of the basic one. Yeah, but seems like I have troubles with the basic one.
And
So
in real life, is that used like that? Like you
No.
use Pytorch? No.
Yeah, I mean in real life you use Pytorch, but as you said, you use Pytorch Lightning for it, and these steps of calculating the output, sending it back, and updating the running the optimizer. This is not done manually. This is done by this library. So you basically specify the structure of your model, the inputs, and then you run it.
Okay. And you said it's a separate library that is responsible for that.
Yeah, it's kind of a wrapper over this library. So Pytorch is doing it on a low level, and Pytorch Lightning is able to do it on a higher level.
Got it.
Yeah. So here they suggest to do different typings. We can try this.
Yeah. Stack Overflow, it's like an old school coding. I see some old school technique.
Yeah.
Nowadays, most people use ChatGPT for that.
Yeah, I'm a bit out of date. So if we try this, no, it's still for long. And could we add? I don't know if we do float. So I'm just doing random stuff.
Sorry, what happened with the TensorFlow? Since if you can speak and write different things at the same time, maybe you can tell us a little bit about this.
Yeah, thanks.
TensorFlow.
Thanks for this. TensorFlow, yeah, TensorFlow is alive. A lot of people are using it, and you kind of do the same exercise on TensorFlow. I think currently it's just a trend that more and more people switch to Pytorch from TensorFlow. And that's why I also decided to try Pytorch. Not that I kind of tried TensorFlow a lot, but a bit. And
sort of same experience, sort of same APIs, slightly different, I guess.
Yeah, I think the idea is the same, but I don't know all the details. But most of my friends who do work with deep learning, they say that they switch to Pytorch and they like it and they don't want to go back. So, and I think it's kind of trending. So TensorFlow before was, I don't know, 90-10 TensorFlow and Pytorch, and now it's maybe 60-40. Still, TensorFlow, yeah, is more used. But Pytorch is, yeah, getting more and more of it. Right. Oh, not really right. So what do I miss from my cheat sheet? Maybe this thing, but I'm not sure if it's kind of help. So when we define the optimizer, we have to zero all the gradients before every pass, and because every time we have to calculate the gradients from scratch, and we want to use the previously calculated, the ones that we calculated in the previous batch. But I'm not sure that it will help. I think it's just completely irrelevant, and it is, yes. Loss function, y calc. Does it say anything else regarding?
In the meantime, I found in Stack Overflow the exact question I had when explaining how optimizer and loss are connected. I haven't read the answer yet, but I will.
Yeah, I hope that's what the thing. Yes, I just kind of put it in the wrong order. the parameters.
Okay. Was a different order of parameters?
Yeah, because the y's are the real values and they are integers. But the y calc is what we calculate from the output, and these are floats. And yeah, I kind of mixed the order. Yeah. Sorry.
No worries. Yeah, that's funny.
Yep. So now it kind of works, but we don't have any output, and we could try to calculate at least something. And to do this, so here we calculate the loss. Value calculated. Yeah, exactly. And here we also can calculate some parameters like accuracy. Calculate the accuracy of our model. Accuracy. And of course, I will use my cheat sheet and how to do it. So y calc. Just a bit. Yeah. So y calc is now the vector of 10 elements. And these 10 elements in the vector, they represent the probability that this is a specific number, or a specific digit that we recognized. And one of these values, one of these probabilities is higher than the others. And that's basically what our model outputs. I don't know, maybe I could, can we do a print to try to explain what I mean? Yeah, it's kind of a lot because we have a batch of 128. Yeah, so basically this is how one vector looks like. It's 10 probabilities. And the highest of them, so currently it probably will be this one. And this means that this vector represents the number 0, 1, 2, 3, the digit 3. So it kind of predicted that this is 3. And now what we want to do, we just want to find this max element. So there's a function argmax. And it will just output the index of this element. And we want to compare it with the real value. And the real value is hidden in here. And we want to know basically, so we go through the whole batch, we do this comparison, and then we calculate how many times in this batch we were right. And then just divide by the length of the batch, so it will be kind of the average accuracy of how we do it. And Yeah, we can basically print it always. And I think now we will have, yeah, so yeah, now it's kind of hard to track. It's just some number. And we don't see any changes like this. And yeah, we kind of already over the time, I would say, but maybe what we can do, dimensional strain. Yeah, I just want to like show us quickly a graph how it changes. Maybe if we can do it fast. Let me think if we can do it fast.
So you want to show how the accuracy changes through epochs when you train the model, something like that?
Exactly. Yeah. So yeah, so basically let's create before every batch. Yeah, just before every batch, let's create this list accuracy train, and then we will just append to this list every value, current accuracy, and then in the end of the batch we do the I hope I know I did not import NumPy. Batch accuracy train, and let me import NumPy. We needed just to calculate the mean. Sometimes we import the whole library for it. So yeah, so basically we go through all the elements in the batch, and we add this accuracy to the list, and after the batch we get the mean of this list. And let's run, I don't know, 10 epochs and see how it will change. And for this we also have to create another one. Yeah, let's say before training accuracy train history. Okay, yeah, now we could run it. And in the end, let's do a quick plot. Oh no. Yeah, so now this stuff is into GPU, but if I want to calculate it normally, I have to send it back. So I kind of do dot CPU. That's all the weird things that I'm not yet familiar with. There's no. Okay. Wait, not this one. This one. On a scale from 1 to 10, how bored are you, Alex?
Where 0 is, what does 0 mean and 10?
Yeah, that's a good question. Well, 0 is not yet not bored. 10 is you're super bored.
Okay. Yeah, somewhere around 0.
Thank you. You're so nice. So nice. Yeah. Yeah, I just want to prepare the plot.
What is still okay? Yeah, a plot would be the graph that just some chart that you want to show these results.
Yeah. Okay.
And does anything left beside this is a necessary step, I guess, but yeah.
To be honest, yes. So we kind of didn't do a validation step. So for now we will see the metric on the training data set. But ideally, after every batch, we should calculate the parameters on the validation data set. And that will be the decider for us. So how good we are for the validation data set. But so basically, we have to calculate this thing for the validation data set and check it on the validation data set.
Okay.
But more or less, that will be it. Let's see if we have some plot in here. Yeah. So so for now, our plot looks like this. So it's kind of going in random directions, which is not good. Yeah. But also it might be because we just had 10 epochs and only a couple of images in there. Ideally, how it should look like, I could show you here. So that's how it ideally looks like, the accuracy. So it kind of slowly goes higher and higher and higher and saturates in some moment.
Okay.
But yeah, today we're unfortunately not yet there, and maybe at some moment we will be there. Yeah, I think that definitely makes sense to create a normal session out of it, and I should be just much better prepared, and we can do it in one run. Or maybe I can do it just off the camera for myself, and not disturb nice people on their perfect Saturday morning.
Nah. Definitely useful anyways.
Yeah, I mean, for me it is useful. Yeah, it's kind of a public shame now how good of an expert in deep learning I am. So now I shouldn't apply for these jobs for quite some time. But yeah, it is what it is.
Okay, that was a roasting, the roasting morning.
Yeah.
But yeah, so yeah, shall we continue that next one of the next times? What would be the best for you?
Yeah, no, I mean, we definitely should continue because there are some other things that I want to do better. So, for example, you can. So now we have a data set of images, but what you do ideally, you also do augmentations of these images. So you take the image, you rotate it, you slightly change the parameters, you change the colors so that the model gets more and more information out of it.
Okay.
Yeah. And it should improve the accuracy. But for now, we don't even have the accuracy.
That's nice. Yeah.
So maybe in one of the next sessions, when my level of expertise is much higher.
What do you think? Yeah, of course, this is just a simple, let's say, simple data set, simple task that everyone solves at some point. Like, if you train this model, like, can it be applicable to any other data set of images, or is specifically for the numbers, for specifically for this data set?
No, it definitely can be. It definitely can be. It's just that our architecture that we picked currently is very simple, and with real images, this architecture probably won't bring us nice results. But yeah, so there are just different architectures for it. But it definitely will bring us something, and probably we'll be able to distinguish like hot dog of non-hot dog.
Yeah. That's a very important task nowadays. To be honest, it's crucial in environment.
I agree. It's still important when you're gonna eat a donut or a hot dog.
No, but thanks, Igor. It was a very nice session. I mean, I think the main point is that we train our brain, especially in Saturday mornings, and for me, it also helps with a long-term memory, to say something like that. So it helps to remember some things and understand at least on some high level what's going on. So it definitely helps. Thanks.
Yeah. Thanks for being here and not running away, and for support. So yeah, hopefully we get better in all the aspects. That's the goal. Ultimate goal.
Okay. Yeah, share it, like it, and follow us. Let's. Yeah, hope to see you soon. Maybe even today's evening. It's
Yeah, join Alex. We're gonna do something.
even weirder. Okay. Bye bye.
Cool.